Swayam Prabha. Digital India. Educated India.
So what we are talking about is general motion in polar coordinates. General motion in polar coordinates. So I am not thinking about whether the particle is moving in 2D or 3D or 1D, but just I am trying to represent the various quantities associated with the kinematics of the particle in polar coordinates. So what we have is, so at theta equal to, well, so this is along the x-axis. So this is my line theta equal to 0, and here we are having a particle which is along the r direction, and we have this another quantity along the theta direction, and we see that this is theta, right? So what we have is that, let us say at any given point of time, the particle P extends an angle theta at the origin, and the distance of the particle P from the origin is r, right? So r is along the direction r hat and theta is along the direction theta hat. So notice that our r hat, this unit vector, so let me just do a little bit of geometry here. So this is 90 minus theta, so we have, this is 90 minus theta, so this is theta. So this particular angle is theta here, this particular angle. Okay, so from here, which means that this one is 90 minus theta, and from here we complete this triangle and we can find what is r hat. So r hat is going to be cos theta I hat plus sin theta j hat. Okay, cos theta I n plus sin theta j. And similarly we can see that theta, well, so 90 minus theta, so that's, yeah, so the geometry is fine. So theta hat, that is the unit vector along the theta direction, is going to be minus sin theta I hat plus cos theta j hat. Okay. So from these two relations I can quickly deduce that my dr hat d theta is theta hat, and my d theta hat d theta is minus r hat. So that's the relation we can quickly deduce, right? So now let us start deriving the formula for velocity in arbitrary space. So v is given by dr dt, and this is d dt of r times r hat. So the position vector points along the radial direction, and so now we need to differentiate using the product rule. So we have that this is r dot r hat plus r times theta d theta dt. So this is r dot is dr dt. Okay. So dr dt is nothing but the speed, because r without any hat or without any bar is nothing but a scalar. And d theta dt is, so we have that this is the speed v, this quantity is speed v times r hat plus r times d theta dt. I can replace it with d theta. Well, d theta, what have we done here? So this is d, well, what have we got here? I think there is some mistake. This is going to be dr hat, right? So this is dr hat d theta times d theta dt, right? And now let us see that this is d r hat d theta is nothing but theta hat using this particular relation. And d theta dt is, we can keep d theta dt as theta dot, or the change of the angle with respect to time, or this is also sometimes called as the angular velocity. This is another new concept that I want to introduce at this point of time, right? Rate of change of angle with respect to time. So now we are ready to write the formula for velocity. So this is speed along the r hat direction, and this is going to be r theta dot along the theta hat direction. Okay. So this is my velocity along the radial and the tangential direction. So this theta hat is my tangential direction, and r hat is the radial direction, sometimes called as the normal direction, right? So now similarly we can find acceleration. We need to differentiate the formula for velocity, which is, we need to differentiate this formula. And let me write down the final formula for acceleration after differentiating. We get that this is r double dot minus r theta dot square times r hat plus r theta double dot plus 2r dot theta dot times theta hat, right? Okay, so that is what we have for velocity and acceleration, the general formula. So let's look at a quick example. So the example says a particle sliding, it's sliding along a groove, along a radial groove. Particle sliding along a radial groove in a rotating table has polar coordinates, right, at time t. We have that r is, so particle is sliding along a radial groove in a rotating table, as the polar coordinate given by r is c times t, where c is a constant, so it's a constant. And then theta is omega times t, and we have omega also as a constant. Okay, and the formula for velocity can be quickly written as, so v is given by it's v times r hat, the speed, plus r theta dot times theta hat, the polar formula. And we see that v is dr dt, so this is nothing but c, so dr dt, so this is dr dt, right? And then theta dot we can quickly differentiate. We get that this is equal to c times t times omega theta hat, right? Okay, so which means that my velocity comes out to be c r hat plus c t omega times theta hat. And again from here we can find, to find acceleration we need to plug everything in the formula. The formula was r double dot minus r theta dot square r hat plus r theta double dot plus 2r dot theta hat, right? And that is what we have, and we start plugging in the formulas. We get that the acceleration comes out to be minus 2ct omega r hat plus 2c omega theta hat. Okay, and so that's it in terms of this example. So in general when we have a uniform circular motion, so general circular motion, which is typically uniform, we expect that r dot is going to be r double dot is 0. So when you have a uniform circular motion, which means the particle is moving in a circle with constant radius. So you don't expect the radius to change. So all these derivatives will vanish, and we have that v is b theta dot theta hat, right? V theta dot theta hat, that is the speed, right, along the tangential direction. And from here we can find that, so that's my velocity, and the acceleration a comes out to be, using the formula, comes out to be minus v square by b r hat plus v dot theta hat. So few slides back we had looked at an example where we found that the acceleration of the particle along the circle was this quantity. That was the case when the velocity, the speed was independent of the parameter time, the t. So, which means in that case v dot was 0, and hence we were getting the same result, right? So this is the formula for the velocity and the acceleration in general along a circle with fixed radius. Okay, so let us quickly look at an example. So the example says the bob of a pendulum moves on a vertical circle of radius b, right? When the string makes an angle theta, right, with the vertical. The string makes an angle theta with the vertical. We need to find the acceleration. Acceleration of the bob, right, and the velocity. If the velocity is given by v square is equal to 2gb cos theta. So the setup is as follows. We have a pendulum which is hanging from the top of a wall, and the pendulum of course has a fixed rod which is attached to the bob, and we have that the bob is experiencing a weight. So this is our acceleration due to gravity. We will introduce this idea very shortly when we talk about gravitation, and then we can quickly see that the velocities of the system is given. So we need to find the acceleration. So the acceleration is, from the previous slide we have that this is v square by b times r hat plus v dot theta hat, right? So v is already given, so I can quickly find what is the r hat component of the radial component of the acceleration, but I don't know what is v dot, right? But I need to find v dot, that is dv dt, the rate of change of speed with respect to time, by differentiating with respect to t, not theta, right? So we use this formula. We see that if we differentiate this formula this v square formula, we get that. So we differentiate with respect to t, right? And we see that this is 2v dot, this is equal to 2gb sine theta with a minus sign times theta dot, right? Okay. So what we have is, what have we got? The pendulum is moving along a circle of constant radius. So we have that v is also equal to b theta dot, right? Because b being the radius of the pendulum, so b theta dot, right? So from here we see that the right hand side of this equation is that this is negative 2g sine theta times b theta dot. B theta dot is v, right? And from here I can find that v dot is negative g sine theta, And so that's it. I plug this formula in this problem and I get my acceleration, which is what I wanted to find. Okay, so then I want to introduce, as promised, I want to introduce the concept of angular velocity. So to introduce the idea, consider a rigid body which is rotating. Angular velocity, right? So consider a rigid body. Consider a rigid body which is rotating. Consider a rigid body which is rotating, and well, first of all, my rigid body is denoted by this curly B. And before even talking about rotating, let me say that the axis of rotation, let us say this axis of rotation is L. And now I say that this body B, curly B body is rotating about this axis L, right? So this is my theta. So we see that at time t, my body B has angular displacement. It has angular displacement theta, right? So at any given time t, the body must have rotated by an angle theta along our given axis L, right? So I can associate theta to be the rotational displacement. So this is the rotational equivalent of Cartesian displacement. Cartesian displacement. Okay? The rotational equivalent of Cartesian displacement, and we say that x of a particle, so this is the rotational equivalent of the Cartesian displacement x, right, of a particle which is perhaps moving in a straight line or 1D, right? So now I am ready to define my angular velocity. My angular velocity is defined omega of the rigid body B. The angular velocity denoted by this sign omega, this letter omega of the body B is defined as omega is d theta dt, and this is going to have a direction along the plane which is perpendicular to the body, right? So let me call this direction as my direction n hat. Let us say that this is a unit vector. Okay, so the magnitude of this angular velocity, which is mod of this omega, is the angular speed. The angular speed which is in radians per second, right? And let us now, so that's a quick introduction of angular velocity. So now let us look at a quick example. So suppose we have an engine. Suppose we have an engine which is spinning at 6,000 revs per minute. Suppose we have an engine, right? So we need to express our speed, our angular speed in SI units, right? So that's a simple problem, but a problem to begin with. So now notice that omega, which is 6,000 revs per minute, is equal to 100 revs per second, right? And at every revolution, the particle is moving 2 pi radians. So this is equal to 2 pi times 100, which is 200 pi radians per second, and that's the answer in the SI unit. Okay. So to begin with, so that's the end of this example. Now let us look at what happens when we have a particle which is on the rigid body what type of given the rigid body having an angular velocity omega, that is the rigid body is rotating. So does the particle have some linear velocity in this case? The answer is yes, right? So what I'm trying to discuss is what is the velocity of the particle. So velocity of the particle of a rotating rigid body. Rotating rigid body. Okay. So we see that the particle P, it moves on a circle of radius rho, right? And well, let us say that we have this rigid body. Well, this body can be anything, but all I want is that, let's say this axis of rotation is given by L, and the particle P is at a distance rho from the origin of this axis of rotation, right? It moves along. As the body rotates, the particle also rotates, which is rotation along a circle of constant radius rho, right? The body can be anything, but all I care about is how the particle is moving, which is on a circular motion. So notice that in this case, the particle, the P will have a circumferential velocity, given by V equal to rho omega, right? And it acts along the theta direction. So it depends on the distance from the axis of rotation, and it depends on the angular speed of the rigid body, right? And that's about it. That's what the particle, so the particle sitting on a rotating rigid body will experience a linear speed as well, which is given by this quantity. Okay. So so I think the concept is straightforward. So there are some examples which I have decided not to discuss, which is very, very simple. So let us now talk about the motion of a rigid body in a on a plane, that is the planar rigid body motion. So rigid body in planar motion. Rigid body in a planar motion, and we see that a body B in a planar motion will have, we have already seen, will have a translational velocity, that is a linear velocity, and of course it will have a rotational velocity as follows. So suppose we have a rigid body B which is in planar motion. The rigid body B is in planar motion if each particle of B moves in a fixed plane. Each particle of B moves on a fixed plane, and all planes are parallel to each other. And all planes are parallel to each other. So if I go back to my previous example of a particle moving in a circle, right? So the particle is moving in a circle. So essentially I can say that the particle is moving, each particle moves in a fixed plane and all planes are right. So if the particle is moving in a circle, the circle, if I extend it to 3D, is representing a cylindrical plane. Now if I change the radius, the particle is again moving in a circle, which is again a concentric cylinder in 3D, right? So all these planes where the particle was moving in a circular motion was essentially over a concentric cylinders which were parallel to each other, right? They were not intersecting at any given point. So that was a previous example. So that is what I meant by by what happens when the particle is experiencing a planar motion on a rigid body, right? So then I can break down this velocity into two components. The velocity of the particle on the plane, the velocity of the particle p is the vector given by the vector sum of a, the translational velocity which is equal to the velocity of the axis of rotation, or let's say the velocity of the center of mass of the rigid body, right? So this is going to be the translational velocity, which is equal to the velocity of the reference point. Let me call everything as a reference point. So what I mean is that suppose you have a rigid body and I want to find the velocity of any given particle on the rigid body, and then it will be the sum of two components. The first one is the so-called Vt, which is the translational component, that is the component of some reference point on the body, let's say C, right? So V at P is equal to V at C, right? Let me call this velocity of the reference point as Vt, right? And then the next component is the rotational velocity, which is the velocity of the body. If we fix the reference point, then it is the component due to the fact that the body is rotating with some angular velocity omega. Okay, so if the reference point C was fixed, then the body was rotating, and the body was rotating with angular velocity omega, right? The body was rotating with an angular velocity omega. For example, if the reference point C is on the axis of rotation, right? So that any point on the axis of rotation will always, let's say, axis of rotation. And let us now, for example, look at, we fixed our frame of reference on the axis of rotation of the body, right? So any motion of the axis of rotation, that is the translational motion, will not be visible in that frame, right? And the only motion of the particle P that is going to be visible on this rotational frame, or this frame which is attached to the axis of rotation, is going to be the rotational velocity. So let us say that this is Vr. So the net velocity of the particle is going to be Vt plus Vr, right? I think a more sensible notation should be Vc plus Vr. So Vc plus Vr, velocity of the reference point.